We've talked finances and customers. Today, we are going to focus on sales KPIs. Welcome to this video on analyzing business data with T SQL. My name is Kevin Fiesel, and I am the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. In the prior video, we took a look at customer key performance indicators, particularly around grouping customers into buckets based on their behaviors. In this video, we will shift to sales-related KPIs, learning a bit more about specific T SQL syntax and analytical techniques along the way. Without further ado, let's go to the demo. Here we are in Azure Data Studio. Today's video will show off a good bit of T SQL functionality while we describe some sales measurements that we can easily convert into KPIs. There will also be some bonus scripts that I don't normally present in the full-length version of my Analyzing Business Data with T SQL talk. The reason for that is, normally I only get 60 minutes in total to go through these KPIs, so that realistically gives me about 5 or 6 scripts that I can show over the course of a talk. I have no such limitations here, which is probably why my average video length in this series is about as long as a Fidel Castro speech. But moving on, let's talk about average time to first conversion. This is a powerful metric in the retail space, especially online retailers. The idea is, how quickly can we get a customer to make their first purchase once they've expressed interest in our offerings? Most often, we track this based on when the customer first lands on our storefront page. In a brick and mortar retail scenario, it's a lot harder to measure this, as typically you won't know any details about the customer until the first purchase. With that explanation in mind, let's take a look at the query. We start off using the apply operator to get the first order date for each customer. Apply has been with us since SQL Server 2005, and the idea is that it allows us, for each record on the left-hand side, to execute a function on the right-hand side. Importantly, function here does not necessarily mean a user-defined function. In fact, in all of the examples you see today, as well as in the next video, I completely avoid user-defined functions, as there is very frequently a performance penalty to using those. Instead, I will create ad hoc functions with the apply operator. Another note here is that the function can return more than one result, and that behavior will be similar to an inner join in which multiple records on the right-hand side match the join criteria for the record on the left-hand side. In that case, our result set will have one row for each match rather than a single row. The two varieties that we have here are cross-apply and outer-apply. Cross-apply is similar to an inner join, and outer-apply is akin to a left-outer join. Note that there is no equivalent to a right outer join or a cross join because of the math behind functions. Functions take an input, do some work, and usually emit an output. We cannot do that work without the input, and thus we need that left-hand side, as that's the input to our function. Even if the innards of the function we apply do not actually use anything from the left-hand side, we still need it as the input to our function. We cannot have a function without an input. It doesn't really make sense. If you want to learn more about the apply operator, check out the show notes below. I'll include a link to a talk I deliver entitled Apply Yourself, in which I go into great detail on the apply operator, giving you a half dozen or so great use cases for this operator. I am a huge fan of apply and do my best to help people understand why. Now let's see it in action. I want to get the first order date for each customer. We could write this query as retrieving the minimum order date and group by customer, but I'm going to use the apply approach for this one. We start off with sales.customers, which I've aliased as C. Then we'll perform an outer apply, indicating that perhaps not all customers have had orders. Inside the apply operator is an ad hoc function, a select statement that retrieves the first order date from the orders table where customer ID matches the ID in the customer's table for the row we care about. As I execute this query, it is running row by row, but it is very important to note that this is not rebar. That is, it is not row by agonizing row. Without going too far down that rabbit hole, let me quickly explain what rebar is and how the apply operator isn't the same. To do so, I'll need to shed light on a weakness in SQL Server versus platforms like Oracle. In Oracle, you can write a fast cursor operating over each record. The database optimizer in Oracle does a great job handling cursors, and so you can think in more of a procedural row-by-row sense. By contrast, SQL Server does not handle cursors or while loops well at all. The syntax is clunky, and the performance is worse than an equivalent set-based operation. This has led to Jeff Moden's famous acronym of REBAR to describe how slow and clunky SQL Server's row-based processing can be compared to a single select operation acting on all of the data at once. But when you dig deeper into the internals of how the database engine gets stuff done, at some point, even in our set-based queries, we'll need to work on a row-by-row basis. The difference is not that one system is entirely set-oriented and the other is entirely row-by-row, but rather that our interface mechanism, that is the variant of SQL we use to query data, has differing levels of support for row-based operations and how the database engine optimizes those operations. And this brings me back to the apply operator. Yes, the concept of the apply operator is to execute some function one time for each row on the left-hand side. But when you write a query like this, it's really no different from a correlated subquery in T SQL, and the database engine knows how to optimize those. For this reason, a well-written query using the apply operator with appropriate indexing will usually be as fast as an equivalent correlated subquery and can often be faster depending on the work you're doing. If you want more details on this line of thinking, check out the Apply Yourself talk. In the meantime, let's get back to average days to first conversion. The core of the query looks just like our first attempt. We have a customers table and use the apply operator to get the first order date for each customer. Then I have another really powerful use case for the apply operator, simplifying calculations. In the cross-apply ad hoc function, I have a query without a from clause. This translates to a compute scalar expression in the execution plan and has zero performance impact over keeping the date diff calculation in the select clause. But what it allows me to do is extract out the calculation for number of days to first order, which is what my date diff function calculates. In the event that the customer does not have a first order, we use today's date. Now, in the select clause of our base query, it's easier to understand what we're doing. We first multiply number of days by 1.0 to coerce an integer into a non-integer. If we do not do this, SQL Server will perform integer division, and we'll end up with a possibly strange result. Then, we take the average of all of these values and cast it as a decimal with 2 digits after the decimal point and at most 4 digits before the decimal. Running this query, we can see that the average number of days to first conversion is 12.19. This might represent things like setting up lines of credit for businesses, sending out inventory sheets, and simply the fact that people are busy and might not always get to their first purchase order the day they sign up. But most people on the business side care about trends and times. Is 12.19 a good value or a bad one? Is it getting better or worse? Are there some factors we might not be considering? For example, Wide World Importer sells novelty items, so there are probably a large number of orders during retail Q4 between Thanksgiving and Christmas. If a customer signs up during that time frame, we might have a longer wait to their first order as the customer is too busy preparing for the busy season. We could speculate all day, but we have the power to investigate. In the last video, I showed you how to create a calendar table. Let's make use of it again. We'll start our query similarly to before, except this time I'll perform an inner join to the calendar table based on the first order date. Then we can get the calendar year and calendar quarter, as well as the average days to first conversion for each year and quarter combination. Running this version of the query, we can see the results. We can investigate whether there are any trends, and if I scroll down a bit, we can see that the average days to first conversion drops considerably starting in Q3 of 2016. Perhaps that was some structural change, such as making the website easier, switching to an online product catalog rather than mailing out a paper copy, or even streamlining the purchasing process. Now let's switch to the next script, average days between orders. This measure can make sense in an e-commerce system as well as an in-person retail system in which you expect somewhat frequent shopping, like perhaps a grocery store or a department store. If you expect a person to make one purchase every 5 years, this measure probably is not going to be that important. The measure uses some of the same techniques that we learned in prior KPIs, specifically common table expressions and the lead window function. We look at the orders table and, for each customer, get their order date and the next order date, specifying where the next order date is not null. In other words, we are going to skip the last order for each customer, as we don't know when they'll order from us next. I also left the calculation of average days between orders alone, not putting it in a cross-apply operator. It's not terribly difficult to understand, but there is a little bit of mental overhead. Running the query, we can see that there is an average of 2.23 days between orders. Now let's expand this to average days between orders on a quarter-by-quarter basis. We take the orders virtual table and join it to our calendar table. This time around, I'll use the cross-apply operator to move the calculation of days between orders into its own pocket of the query, making it easier to understand the calculation in the select clause. Running this, we can see days between orders over time. And once again, the data blows up in Q2 of 2016. Clearly, our sales team has done a fantastic job of increasing order frequency. Or, well, in reality, the stored procedure that Wide World Importers comes with in order to generate more data doesn't generate data following exactly the same patterns as what we already had in the tables. But I like my just so story a bit better, so we'll stick with it. Our third metric is average order value. This is extremely common in retailers of all sorts, as it gives you an idea of how much money you can expect to get from a single customer purchase. There will certainly be variance in this. Think about a standard department store. On one trip, I might go there and buy a single book for $15. Then on my next trip, I'm buying gifts for a bunch of people and spend $250. But even with that level of variance, it's still useful for the department store to get an idea of how much the average customer is spending. The first part of average order value is to calculate the order value. We first start out with calculating the value of an order, which is revenue. We have the orders table and we can join to the order lines table. Then we multiply the order line quantity by its unit price and we get order value. So obviously the average order value is the average of these order values, right? Well, running this query gives me an answer of $776.82 as the result. If I go to the sales team and talk to them about this, they are shocked the number is so low. I mean, their incentive bonuses start kicking in at $2,000, so it's wild that corporate is expecting them to work so hard and so rarely get incentives. But then each person also thinks, hey, wait, I'm getting incentives pretty frequently, so I must be the best sales agent out there. Well, let me burst that bubble. The problem is, we're only calculating the average order line value, but one order may have multiple lines. What we need to do is aggregate this data by order and then take the mean. Fortunately, as we learned in the financial KPIs video, revenue is an additive measure across orders, so doing this is easy. In a common table expression, we once again join orders and order lines. We are going to take the sum of revenue as well as the order ID and group the results by order ID. Now we have the sum of order line revenue per order. Then in the base query, we take the mean of those summations. Now the average order value is $1,806.16, and that helps explain why incentives kick in at $2,000, yet most sales reps regularly get incentives. It's not that everyone's a wizard, it's that the incentives are actually pretty easy to meet. So naturally, the next question becomes, what use can we make of this data? Well, we could look at average order value sliced by sales territory and see if certain regions of the country are easier to sell to. This time around, we have sales territory and order as well as revenue. Again, revenue is additive across these dimensions, so we don't have to worry about mangling any calculations. Running the query, we can see that all of the regions are right within the same price range, though I do appreciate some thrifty Midwesterners driving down the average order value. We can also get a little fancier. Let's look at specific customer and average order value over time. First, we'll look at the orders for customer 13. Running this query, we can see some long-term consistency in ordering, making a few orders in some months and skipping months otherwise. Occasionally, there is an extra large order, like the one on May 13th of 2013, so this appears to be a perfectly normal customer. But it's hard to draw conclusions here because the variance between order values is just so high. We can smooth this out using a technique known as a moving average. A moving average is simple. We look at a fixed time window, such as over a few months, and take the average of everything in that window. Then we shift the window over a bit. Typically, we want to have some amount of overlap in our windows. That way we can see trends more easily than individual orders, and there's a better chance of spotting something than if we use tumbling windows, where each window covers a unique span of time. Given that I've used the term window several times in the last paragraph, I'm sure you can figure out the technique we'll use to calculate these results. That's right, a common table expression. Well, okay, a common table expression whose virtual table result set we're going to analyze using a window function. Specifically, we're going to use 4 window functions. The first one gives us a running total. The idea here is that we want to sum up the revenue across each order that has already happened, so we order the window function by order date and order ID. By default, with sum and an order by clause, there is a hidden additional frame criterion, specifying that we want the range between the first order in our set and the current row. I have a separate talk on window functions that helps explain that better. Details are in the show notes. For now, though, I'll just state that this is an implicit part of the window function and leave it at that. Next, we have the average of all orders from the first order the customer made up to this one. This is one way to calculate a moving average. It's easy to do, but it comes with a major downside. It overweighs older records. Older orders will show up in almost every row's calculation, whereas newer orders will show up in subsequently fewer. Furthermore, there may be differences in customer behavior over time that this approach smothers, as it takes a long time for new behavior to outweigh old behavior. Instead, what we can do is change the frame. I mentioned that the default is a range from the first row to the current row. Well, let's specify that we want the 9 prior rows up to the current row. That way we get the 10 latest rows. So why do I specify 9 instead of 10? The reason is that the current row is different from preceding rows. So if I want exactly 10 records, I need to specify the current row as well as 9 additional. Doing that, I can calculate the sum and the average. Let's run this query. We can see that things start off the same, at least for the first 10 rows. Then we'll have some divergence between the last 10 and the overall values. If I scroll down a bit to the beginning of 2015, we can see an average order value that is several $100s above the overall mean, indicating some recent and rather large purchases. But by March, we are again below the overall mean, as we had a stretch of smaller purchases for this customer. In other words, we can see the trends much more clearly by looking at the 10 latest records. And one last thing that I'll show regarding this KPI is a quality of life improvement in SQL Server 2022, assuming you have your database compatibility level set to 160. You can see the 4 window functions that we looked at. We have 2 matching pairs of window definitions, and that's a little bit messy. If we switch from the latest 10 to the latest 5 records, I have to make sure to get it right in both locations. Now, this may not sound like much, but it's really easy to mess up when you have a series of window functions in a larger query. Thus, in SQL Server 2022, we have the window clause. This query is exactly the same, save for the use of the window clause. First, I define ORD as a window, specifying that we are sorting by order date and then order ID. After that, I specify ORD10 as the ORD window, but then I clarify that we only want the 10 latest rows given that ordering. Finally, in my select clause, we specify those windows here, making the statement considerably shorter. And if I run the query, the results are exactly the same. It's also the same query performance from the database engine, so we don't need to think about whether one approach or the other will perform better, because ultimately they're doing the same thing. And while I'm going on about great things in SQL Server 2022, let me bring up one more of them with our final metric, customer percentiles by sales. Prior to SQL Server 2022, we had a window function called percentile_cont, which generates a continuous percentile. For example, you could generate the 50th percentile, which is the median. You could also generate arbitrary percentiles like 75th, 90th, 95th, or 99th percentiles. This is quite useful when dealing with skewed data sets, as a small number of large values will not skew the median like it can the mean. The problem with percentile_cont, or its discrete cousin percentile_disk, is that they're slow. For the dataset and wide world importers, I could generate percentiles using the window function technique and it'll work fine. But once you get into millions of rows, they slow down considerably. And if you're dealing with tens or hundreds of millions of rows, these functions are either horribly slow or simply will not complete. This is where approximate percentiles come into play. This is an approximation of the percentile accurate to within about 1.33 percentage points of the actual value, 99% of the time. For most analytical purposes, being plus or minus 1.33 percentage points of the correct answer is usually good enough because we're generally looking at orders of magnitude or significant trends. To play it safe, you would want to make mention in whatever reporting tool that you're using that your calculation comes with an error bar. Even so, this is orders of magnitude faster than the percentiles cont approach, so it's very practical for large data sets. Let's see how it works. We start off with a common table expression indicating total revenue by customer. Then, in the percentiles common table expression, we generate approximate percentiles. I am going to give us 6 numbers here. The first is the minimum, or 0th percentile. Then we'll include the 25th, 50th, and 75th percentiles. A standard 5-number summary would then include the maximum, or 100th percentile, but I'm also going to throw in the 95th percentile for free. It's a buy 5, get 1 free deal. This looks similar to a window function, but it's actually something else, called an ordered set function. You can tell this because of the within group syntax. There are only a few ordered set functions available within T SQL. The first one that became available was string add, which showed up in SQL Server 2019, and I am excited to see the number of ordered set functions grow over time. Anyhow, in our base query, we start with the percentiles virtual table and rename some percentiles to indicate that we have the minimum, median, and maximum values. We also generate an interquartile range, which is the difference between the 75th and the 25th percentile. Half of our data falls within this range, and the other half falls outside of it. If I run this query, we can see that the minimum customer sales amount is about $10,026.65, and our maximum is $2.6 million. Our median is $2,241,334.35. We can see that our interquartile range is pretty tight, and we don't have a single whale of a customer propping us up. Scrolling down a bit further, we can see that we can, of course, introduce other ways to slice this data. For example, let's say that I want to slice by sales territory. Now I'll include the sales territory along with the customer ID. Customers are in a single sales territory, so we're not actually expanding the grain of the query. Let me quickly show you by scrolling back up and selecting the contents of the first customer sales CTE. When I run this query, we can see that there are 735 total results. Then, if I scroll down to the current query, I can run its customer sales CTE contents and see that we still have 735 records. Thus, we maintain a consistency between queries even when adding in the sales territory. Next, the percentiles common table expression is slightly different from before. This time around, I'm introducing sales territory and then performing the approximate percentile function calls. Because these are ordered set functions, they take into account the group by clause, and so we're going to group results by sales territory and then perform the percentile approximations. This will give us a minimum for each sales territory, a 25th percentile for each sales territory, and so on. I'm also including the number of customers per sales territory, as I imagine there won't be an even split between these territories. The base query is the same as before, so there's nothing new to see here. Instead, let's run this entire query and get our results. We can now see our results broken out on a per sales territory basis. There might be some interesting ways of reading through the data and digging into differences between regions, but that would be a topic for our business people to investigate. And those were the sales KPIs. Along with learning about average time to first conversion, average days between orders, average order value, and customer sales percentiles, we learned about several techniques today. We got to see 2 great use cases for the apply operator, looked at how to generate running totals and moving averages using window functions, took advantage of the window clause in SQL Server 2022, and also tried out the approximate percentile function in SQL Server 2022. In the next video, we will wrap up this series with some Avidity-related KPIs. We'll have links and show notes in the description below, and until we see each other in the next video, take care.